Um, um, Okay, so what you were mapping on those fossil localities, you can also predict some of it based on just overall geological mapping of Minnesota. So here's a clearly rather old copy of a geological map. But this is roughly the ages of different exposures that they found in the rock in Minnesota. So you can see here we have the map units, so we can see that those are a bunch of our periods essentially. And here we have that correlated up with what kind of rock. So we can notice, so you probably more notice this from the mapping activity that we just did. Right here where we are along the edge of Lake Superior, we actually have a bunch of Precambrian stuff. So where we are is super old. Someone actually told me that Lake Superior is where they go sometimes to try and study the moon. I don't remember who said it, and I have not yet tracked down a scientific paper for that, so I'm not saying that super officially, but you can understand why that might be true based on the age of the rock that's exposed here along the lakeshore. Okay. So starting way back in time, we're going to begin with the Hadean. So the Hadean was named after Hades, basically because they thought, in theory, that at the beginning, life on Earth was pretty hell-like, fiery, unstable, toxic, hot. We're going to be talking about that a little bit today. So the Hadean is from about 4.5 billion years ago to about 4 billion years ago, and it's going to be followed by the Archean. So some of the evidence that we talk about for life kind of today and on Friday, some of it is arguably part of the Hadean versus the Archean, and you'll find kind of different arguments about when exactly we start to see the first signs of life. All right. So talking about ages, we mentioned last time that one of the ways we date things is through radiocarbon dating, or sorry, through radioactive decay, I would say. Radiocarbon dating we use for modern stuff, but that doesn't work billions and billions of years ago. The time scale isn't right. So what we use to try and date the age of the Earth and date the age of the Hadean is through something called zircon. So zircon is a mineral that forms out of zirconium, silicon, and oxygen. It crystallizes basically from magma. So we're thinking about fiery volcanoes, eventually cooling and becoming rock. Okay. So there's some neat properties of zircon. So zircons are going to end up embedded basically in other forms of rock, but they withstand super high temperatures. They don't really weather. So it's not that zircon is like the only thing that was probably around in the Hadean. It's that it's so hard to break or melt or get into the inside that zircons, we think, really haven't changed much. So when we date a zircon, we think that the date that we get for that zircon is the actual age of the zircon, and we don't have to worry so much that stuff got inside of it or it melted and became something else. So as zircons form, they cool and they add outer layers. So you'll often see kind of like stripes of time in zircon, and little bits of zircon get embedded in other parts of rock. So the super helpful thing about the formation of zircon is that it really likes uranium. They have kind of compatible shapes. So uranium gets integrated into the crystal structure of the zircon. Okay. But zircons really hate lead. It's really incompatible with their crystal structure during formation. So when you have your originally formed zircon, it's going to contain some uranium, but is absolutely not going to contain any lead because it's repelled all the lead during its formation. But the thing is, uranium turns into lead over time. It decays. That's part of its decay process. So through doing some math, when we're looking at a zircon in the modern day and we want to figure out how old that zircon was, we can look at how much of it is made up of uranium, which would have been the original state, and how much of it has decayed into lead. And knowing how half-lives work, and we actually know half-life of uranium partially through experiments during nuclear testing, essentially. So uranium's involved in that, so we know a lot about uranium because it was very interesting to us. So we can use those half-life calculations to date that piece of zircon. So here is a picture of a rock with zircon embedded in it. So the oldest zircon that we found is from somewhere called Jack Hills in Western Australia. So we have these big old rocks. They start as basal conglomerates and become medium-grade sandstones. We're not geologists, we don't need to know about that. But basically, we've exposed these layers of rock with the embedded little zircons. They're super tiny. So they're about the width of a human hair. So here we see a zircon from Jack Hills next to a human hair on a penny here. Okay. And we're going to practice just doing a sort of simple half-life radioactive decay calculation to get a handle on this, because we're going to talk about dating using decay multiple times throughout this course. So we want to get an idea of how that works, which means I have another sheet for you. What I'm giving you is a kind of simplified problem. At the top, you can see more about the series of sort of intermediate species we go through as uranium decays into lead. This is a neat little exercise that doesn't focus on the intermediate species. And you can take a quick look at the real data, which is not there. So the slide just says the same thing as this little worksheet does. You don't need it yet for this exercise, but the paper we're going to take a look at data from next. So a note that may not be obvious is going to appear a couple of times. Those units on there, GA, that's how they write trillion. I don't know what the G stands for, but let's walk through this a bit together. Got my annotation tool. Okay. So in this example, let's think about the formation of the zircon. So how much lead was in there when we started out? In the formation of a zircon.
I would say when you got it, or
when the zirconium, or when the zircon originally formed. None. Right? Does that make sense? So that's why we can do this math, why it's helpful. So we're going to have 0 atoms of zircon when it starts out. Okay. So then, if none of that stuff was lead when we started out, how much uranium did we have? So go ahead and look those numbers. Right. So we take from the example, we have the 6 trillion atoms of uranium that we have now. And currently we're looking at 3 trillion atoms of lead, but we know those must have started out as uranium because lead got pushed out of zircon during their formation. So we're going to have 9 trillion. Then the next piece we need to know is how much of the uranium we have left versus how much we started with. So we can just do this as a fraction. So we have how much? So we have 6 trillion uranium, and we started with 9 trillion, which can be 2/3 actually. 6 divided by 9, we can even just write it that way because we're just looking for an age. Yeah. So 2/3, 66%, whatever. Okay. So this next piece, we're going to just make an estimate using a chart. So we have our theoretical decay of the uranium over time. So we should be able to go through and look at that percentage of uranium remaining and find on that decay line where we land. Okay. So we're going to find a little point. So anybody who was looking for that about 66%, well, what do we get there? We're just reading the graph. Something like that. Yeah. So that pulls us to 2.5-ish billion years for this. Cool. So if we want to get a quick sense of things, we don't even really have to do the math. We can just look at the decay series like that. Okay, so 2.5 GA. But if we do want to do it out, we can. All right. So we are going to, okay. So first, over here on top, NT is how much uranium we have right now. So that's going to be our 6 trillion. And we're going to cross out these units in a second, so I'm not going to write them out, but carefully. Okay. And N0, 0 is our initial time point. So when we form the zircon at time 0, we just wrote that we had 9 trillion. Okay. So then our formula here for our radioactive decay for our half-life. So for our half-life, we're going to have our time. I'm going to leave that as a T, divided by our known half-life for uranium, which is 4.47 billion years. So as we go through, I'm going to just cross out our trillions and reduce that to 2/3. Okay. This is now 2/3. Okay. Okay. So to get our exponents down, we're going to need to log stuff. So we're going to have log 2/3. I got equals log 1/2 times our exponent, so t divided by 4.47 billion. And then we just reshape it. So we're going to divide by log of 1/2, and then we're going to multiply by 4.47. So log 2/3 divided by log half times our half-life. Should get us an age of this imaginary zircon in billions of years. Somebody want to plug that in? Just plug that in already. Yeah. So that's how we get our date of this zircon. So this one specifically is not our oldest zircon ever, and they're not all super old. That's why it's special that we found these specifically in Western Australia, the really, really old ones. And that's also kind of why we can say with certainty how zircons formed, because some of them like to see that formation. But this is overall how we would do that dating. Okay. So this will leave us actually here for our homework. I'm not going to ask you to do this in detail on the real data because it's more complicated when we have this whole dictate series. But the paper itself, where we got this date from the Jack Hill zircon, is really short. It's only 4 pages. So I do want you to take a look and just kind of skim for information so that you get an idea of what kind of data they use to make these estimates about the really early Earth. So you're going to look at what major topics are in here, what the data are, like what the types of data are, and how they're related to those major topics and findings. And I would say there are probably like 2 major topics in this paper. And before you go in, it is dense. So I would recommend planning when you're reading a research article, remembering like what part you should look at kind of first, second, and third, and what parts you're going to just kind of skim and leave to the end of the meeting. Yeah. Which maybe we should discuss. Have you guys talked about reading research papers before in your other classes? Okay, cool. All right, so we're not gonna read the whole thing. We're gonna read like abstract figures and conclusion are generally where to start, and then kind of fill in the gap. Okay, cool. I'll take a quick look at that next time and then move forward.